I'm going to talk a little bit about my QRP antenna tuner. This idea came about. This is, I have to say, it's not very original, but there is some originality and some thought that has gone into this. This is, again, it's another boost for the DIY radio group. Our project that we did prior to the QRP power meter was a transmitter, which was the Tuna 10S. And I built one of those, and there's a little picture of mine in a little plastic box I got at Tap Plastics. And the total cost for the parts for this little transmitter was about $25. And it puts out, about half a watt. And one thing it doesn't have a built-in tuner. And in order to maximize the efficiency of this transmitter, you should have an antenna that matches the impedance, matches the output impedance of this transmitter. So I wanted to have some kind of a matching unit to be able to do that. And hopefully it was not going to cost any more than the Tuna 10S itself. So that was a pretty tall order. So I did a Google search and for a QRP tuner, and it came up with these automatic tuners. There was a Chinese one called the ATU 100, which is $114. The Elecraft T1 kit was almost $200. The LDG has a really nice automatic QRP tuner, the Z100, and that's $149. That's way multiple times the cost of the Tuna 10S. So then I looked at the manual tuners, and this is not an exhaustive list of them, but the 4-state QRP tuner kit was $45. The MFJ 9201 QRP tuner is assembled, but it was $64. And QRP guys had this multi-Z kit, which was $40. And then there's another one I found on eBay and on Amazon, which was the Zerone, or the manual days kit, and that was only $15. And I said, wow, that's awesome. I'm going to try and go with that one maybe. So just a little comparison of some of these different kits that the kits that I saw. This is the 4-state QRP tuner, and the specification says it'll take up to 10 watts. It'll run 80 through 10 meters. It has these two little LED lights. One that lights for forward power, and the other one it dims when you've got a low SWR. So that's pretty neat. And the design is, and the documentation is very clear. It's by Dave Kripe, NM0S, who is a great kit designer who has done a lot of presentations in conventions and on the QSO Today expos. He's a wonderful guy, and this is a very well-tested kit, and it has very good reviews. This is the MFJ 9201. It's a little pricey. It's 100 watt intermittent, so it's not really a QRP only, but it does also claim to have 80 through 10 meters. And nope, does not have an LED SWR indicator. That you have to cross that out. That's a mistake. But the manual is online if you want to look it up. And then let's see, QRP guys has a multi-tuner kit, and this one is $40. Did I do that one already? No, I didn't do that one. That one's 5 watts continuous, 10 watts intermittent, 40 through 10 meters. It also has an LED SWR indicator and has a nice assembly manual online. And then this is the one that I decided to go with. Actually, I had it on sale through Amazon. It was $13. And since I have an Amazon Prime account, I was able to order it and get it the next day delivered, which was another bonus. They claim 5 watts continuous power, 15 watts intermittent. It'll actually cover 1 to 30 megahertz. So theoretically, it'll also cover 160 meters as well as 10 meters. And it does have an LED SWR indicator. But the cons against this was there were very discouraging online reviews. VK3YE, Peter Parker put one together, and he absolutely hated it. Said it didn't work the way it was supposed to. And the manual is in Chinglish, and it's got a lot of errors in the translation. Many people said they would try to build a thing and it wouldn't work. So I decided I'm going to go ahead with this anyway, because you can't lose very much, for that price. Maybe you don't follow the instructions, but figure out why the thing doesn't work and get the thing to work. So just use a little bit of noodle power there. And these are the kit parts that it comes with. You have this enclosures, plastic enclosures, completely undrilled. So you have to drill the holes to mount all the parts. And it comes with the BNC connectors, a couple of knobs for these polyvaricon capacitors, LEDs, some capacitors and resistors, a little PC board, which is used for the SWR sensor circuit. And it's got a 12-position rotary switch, which is for the different inductance values. And there's a toroid ring, which is used for the main inductor in the matching network. And there's a small little toroid here, which is used for a pickup transformer used to feed the SWR sensing circuit. You got a little toggle switch and then some enamel wire and regular hookup wire. And then these things are labels. What you do is you put the label on the box, and then that's a guide for you to drill through. And the label also serves to label the different controls that you mount in there. So problem is that these labels, you have a few words here in English, but most of the other labels are in Chinese. And I think this contributed to the problem of the reviews, where people had no idea what they were switching one way or the other, or what goes in or out, because that was all in Chinese. Well, let's go about the circuit description. It's a standard T network tuning unit. It's got two variable capacitors and one variable, it's a switchable inductor. There's a resistive Wheatstone bridge on the input. And the way that works, when the antenna impedance is 50 ohms, the bridge output is 0. It's balanced, so there's no voltage appearing across the primary of this toroid transformer. And the other side of the transformer goes to a little rectifier circuit that feeds the LED light. So when you have a perfect match, there's no voltage, therefore the light just goes out. And then when your SWR is high, which is the impedance is far away from 50 ohms, you'll get a voltage there, which will light the LED. So you tune the thing for minimum light on the bulb. When you do put the circuit in, it causes 6 dB attenuation, and you only switch it in to adjust for the minimal SWR. Then you're supposed to switch it out. And that's one of the other problems on the video. Some of the video reviews of this is people had no idea that you had to switch the sensor circuit out, and they said, oh, this thing causes a tremendous drop in your power output. Well, it does that if you leave the sensor in the circuit. Here's a schematic diagram. Again, this is the input here. Here's your double pole, double throw switch. When you're feeding it straight through without the sensor, it just goes to the T network. And this is the Wheatstone bridge here with the little transformer that steps up the voltage that it picks up here on the Wheatstone bridge, and then it's rectified through this diode. And we've got a little current resisting limiting resistor to the light emitting diode. Now, one of the problems here with the original schematic is this is the way they explain how to wire up this switch to the coil. And what they did was for the minimum resistance, which is where I'm sorry, I have to go back here, where this wiper contact is all the way at minimum resistance. They actually had it at a point where there was 10 turns on the coil. And then down at the point here where it was supposed to be a maximum inductance, you had these like 1 turn, 2 turns, 3 turns between the contacts. The error with that is that you need the fine tuning on the inductor where you are at minimum inductance. So this was inverted. And if people wired it up this way, they would have very much difficulty getting the thing to tune properly at the higher frequencies, because they wouldn't have a fine adjustment of the inductance. So we had to flip that around in order to get the thing to work. And this is just a curiosity. This is the 4-state QRP tuner. It's almost identical schematic diagram. There's the T network right there. And then this is the Wheatstone Bridge. So you see, it's pretty much it's not a very original circuit. It's one that's been very much copied many times. So I had to do a wiring correction on this inductor. And again, I did the turns between the switch contacts, the smaller number up here, where the inductance is the smallest values. And this did work. So I was able to get this thing to work. Now, polyvaricon, people may have not heard of this word before. That's a polyethylene film dielectric variable condenser. That's where that word comes from, polyvaricon. These are little variable capacitors that are made of plastic. They were very common in transistor radios that used these devices and coils. Nowadays, these radios have everything solid state, all varactor tune and stuff. So you very rarely see these very much anymore. But they're still out there, and they're a dime a dozen. The Chinese make an awful lot of them. So since they're so cheap, they were using these in this project. They don't have a very high voltage. They can't withstand very high voltage because they have this little thin sheet of polyethylene film between the plates. And those would arc over very quickly if you put any high voltages on them. But for a QRP application, there's no problem with them. There are two sections. One of them is for the oscillator and one is for the antenna input of a transistor radio. But if you parallel them, you get a total of about 200 picofarads on each of these, which works perfectly in this circuit. The other thing was these knobs that they provided. Now, these polyvaricons, as you can see, they have a really peculiar way of having to attach a knob. It's this little tap hole here in the center, and then it's this little nubbin of a type of a shaft. And you can't really stick a regular knob on there. It has nothing to grab onto. So what they did was they rigged something up where you have this screw that goes through this knob that has a hole down the center, and then poking the bottom of the screw out through here, you would screw that into the capacitor and hopefully have enough friction so you'd be able to turn it both ways, left and right. Well, this is the top here is the hardware they gave you. And first of all, this nut did not even mate correctly with this screw. So this was not going to work. When I did get the correct, let me back up on there. When I did get the correct nut, which was an M2.5 that I was able to find at Ace Hardware, you could turn it to the right and it would turn the capacitor to the right. But if you turn it to the left, it would just completely unscrew out. There was nothing grabbing onto that little shaft to turn it backwards. So I fixed that by adding a little tooth lock washer here. And you tighten that on there, and it digs in enough into that little brass shaft there that gently you can rotate it either way. So this worked very well. There are some other fixes where you could do a 3D printed shaft that fits over that, but I don't have a 3D printer. The SWR sensor board, this is the circuitry for the SWR sensor. There was an error in the printing on here too. They had this is the toroid transformer was supposed to go in here. It was supposed to be 2 turns on this side, the input, 5 turns on the output, because it's stepping up the voltage. They had this labeled in reverse. And if you did it this way, you would have too low of a voltage to light up the LED, and you would think the thing didn't work at all. So I had to make that correction. And these are the Chinese labels. Actually, where here it says like SWR indicator and bright, high SWR, dim, low SWR, those English words were not there at all. All there was a Chinese labeling. And this was the switch on the top, SWR position and normal position for the toggle switch. Again, the English letters were not there. It was just Chinese. I had no idea what this was all supposed to mean. I guess I could figure it out by looking at the circuit. But if somebody built it and tried to figure out what was going on, they would completely be at a loss. So I used my Google Translate app on my smartphone, which you can flip it over to use the camera, point it at that Chinese printing, and it actually shows you right on your screen what it's saying, so you can translate it into English. So I added that onto the label. So able to use this thing properly. If you didn't do that, you might even say the thing didn't work because you didn't know how to use it. And then here's another thing. The sides are the input and the output. And one is for the radio, one's for the antenna. And if you didn't have those English words there, you could turn the thing, you can hook the thing up backwards. And then the SWR circuit would be in reverse and it wouldn't work at all. So you would think the thing wasn't working if you had the thing connected the wrong way. So we did put together the project and I drilled all the holes, mounted all the parts. And this is to show you the two polyvaricons. In the center is the tapped inductor. I had to wind a certain number of turns of the magnet wire around the toroid and then make taps that I have to scrape the enamel wire off and solder them onto each of the contacts of that 12 position rotary switch, which is behind that toroid. And that was one of the major projects putting this thing together. You'll notice that the BNC connectors on the left and the right, I took a piece of number 14 solid, let me back up here, solid wire, copper wire, and I just ran it along the side here, connecting the shield or the shell of both of those BNC connectors together to give a low impedance path. And I also used this as the ground connection for the network inductor. So, and also for the wiper connector on the rotary switch. So this was a way to get a good low impedance connection there. And these are all the other wires. It's a very simple circuit. And this is the front again of the unit. So I went ahead, I put the thing together. I wanted to do a little test of efficiency to see if this thing was going to be wasting a lot of my milliwatt power or if it worked at all. So I hooked it up to my NanoVNA, and a lot of us do have these. And if you don't have one, I do highly recommend you get one. There's just so many good things you can do with the NanoVNA besides testing antennas. And one of the things you can do is tune a filter or a matching network like this. So I take the output of channel 0 of the NanoVNA and I put that to the input of the tuner, and then the output I feed it to channel 1 on the NanoVNA. And all you have to do is then adjust the band switch and then the two capacitors for a minimum SWR on the frequency that you're testing it at. And then it will also show you how much of your power is getting through from one side to the other. So it's telling you what the loss is in dB, and it's really cool. This is one test that I did. I'm using, of course, the NanoVNA Saver, which is a PC app that connects to your NanoVNA so you can get nice big pictures on your computer screen. And this was a test at 10.2 megahertz, which is around the 30 meter band. And if you can see here, the SWR there was 1.003. And the way you know what the loss is, you go to this number S21 gain, and it's minus 0.934 dB. So it's almost 1 dB loss, which is not a big deal. So it's halfway decent. I went ahead and I did this testing on all these different bands, 80, 40, 30, 20, 15, and 10 meters. And comparing the all the VSWRs, the SWRs were pretty low, like right by 1.0, pretty close. The gain here was on 80 meters where I had the most loss. It was minus 1.7 dB, almost 2 dB. So I think the problem there was the inductor is a pretty low Q at that frequency. So it's a little bit lossy there. But on the other frequencies, like here, 30 meters, 20 meters, it's 0.5 dB, 50 meters, 0.3 dB, and 10 meters is 0.3 dB. And I think this is going to be very close to what some of the other antenna tuners you see out there on the market. They're always going to have some sort of insertion loss. So I'm going to just say the conclusion that I found from this experiment was, despite misleading instructions, a lot of discouraging reviews on the internet, and really bad translated Chinglish instructions, you still can get this thing to work. And it's a fun little box. Here it is. So, and for $13, I couldn't go wrong. Got a little thing that mates up with the Tuna 10S. And that's the end of my presentation. Thank you.
Thanks, Carol. Any questions for Carol? All right. So while I'm presenting my section, Phil, do you want to email your scores across to Carol or enter them?
I already did.
Yeah.
Do you have them, Carol? Have you seen my email?
Oh, did you send them already?
Oh, I sent them several minutes ago.
Oh, okay.
I had
In
a
fact,
question
just
for
as she was
Carol.
starting her presentation.
Can you folks hear my question for Carol?
Yeah, go ahead.
Yes.
Yeah, it's Wilson, N6EMF. Nice presentations out there. And the question I had for Carol was when she was finding those problems with the coil orientation reversals, did you do that by visual inspection, or was it after you put it together and you had to troubleshoot it?
No, I was very suspicious of all of the instructions to begin with. So I analyzed this circuit just looking at the schematic and looking at the instructions, and I knew it wasn't going to work. So I did that even before I put it together.
Oh, that's very good. So yeah, thank you for sharing that. I was wondering how you knew. I just couldn't imagine you going ahead and finding all those bugs and then having to desolder things and turn things around. So that was very clever approach. Thank you.
You're welcome.
Very great when you have the tools and you know how to use it and the skills to do it. So good job.
All right.